Good morning to everyone. Last video we have discussed about the different types of coordinate systems. So in this video we have going to discuss about we can solve the one-dimensional finite element problem in the bar conditions. We want to find the primary unknown variables. Based on the primary unknown variables, we can find the secondary unknown variables. So let's we go for a problem. Determine the deflection of stepped bar. So here we are going to solve the stepped bar, and then we want to find the primary variables of deflection. The bar has uniform thickness of 15 mm and breadth at element 1 is 100 mm, and then element 2 will be 75 mm. So they're having a two variable cross sections. One will be 100 mm and another one will be 75 mm. Also determine the element stresses and reaction force. So here we want to find the secondary parameter of stresses and reaction force. So the image is given. In this, the bottom portions will be a breadth of 100 mm and then thickness of 15 mm. Length will be 120 mm. In top portion, the breadth will be 75 mm, thickness will be 15 mm, length will be 150 mm. And then load is acting at the top portion, which has 75 kN away from the objects. And then the constraint will be given for a bottom. And then Young's modulus of this object is 200 gigapascal. So first we want to do a discretization. Based on the material properties, the discretization will be considered for a single because they have an uniform material properties. The Young's modulus will be an uniform. So we won't do it as a discretization. And then loading conditions and constraints. The loads and constraints will be acting at the end of the objects. So based on that, we need to bother to do the discretization. Next, geometrical parameters. So based on the geometry, we want to discretization of two elements. So the bottom portion will be an 100 mm breadth, and then the top portion will be an 75 mm breadth. So based on this geometry, we want to do the discretization. So now we have discretization into two elements. So bottom will be an element 1 and then top will be an element 2. And then node numbers will be an, for bottom the node will be an 1, mid portion node will be an 2, and then top portion will be an node number will be 3. So the element 1 has a node of 1 and 2, element 2 the node of 2 and 3. Here the element 2 will be sharing of element 1, so node 2 will be sharing of element 1 and element 2. The finite element equations for finding the stiffness matrix, that will be an AE divided by L, 1 minus 1 minus 1 1. A means area of the particular elements, E is in Young's modulus of the particular elements, and then L equal to length of the particular elements. In bottom elements, we want to find the area. For rectangle, we want to find the area means area breadth into thickness. So the breadth will be 100 mm and then thickness will be 15 mm. Young's modulus will be 200 into 10 to the power 3. LE will be 120. So after multiplying and dividing, the final value will be 25 into 10 to the power 5. That value we can apply into an inside of the matrix. So 25 into 10 to the power 3 into 1, 25 into 10 to the power 3, 25 into 10 to the power 3 into minus 1. So minus 25 into 10 to the power 3. Again minus 25 into 10 to the power 3, 10 to the power 5, 25 into 10 to the power 5. So this is the element 1 equation. Next we go for an element 2 equation. The breadth will be 75 and then thickness will be 15 mm. Young's modulus will be 2 into 10 to the power 5. Length will be 150. So multiply and divide, we get this 15 into 10 to the power 5. So 15 into 10 to the power 5 minus 15 into 10 to the power 5 minus 15 into 10 to the power 5, 15 into 10 to the power 5. Then we want to assemble the global stiffness matrix, both the equations. So 25 into 10 to the power 5 minus 25 into 10 to the power 5, 0, minus 25 into 10 to the power 5, 25 into 10 to the power 5 for node 1 and node 2 will be 15 into 10 to the power 5. and then minus 15 into 10 to the power 5, 0, minus 15 into 10 to the power 5, 15 into 10 to the power 5. Thank you.